Welcome to qnawire.
For this problem on the topic of sources of magnetic fields, we are told that a horizontal wire carries a given current and a second wire is placed below the first and it is made of copper. It is also parallel to the first and is kept magnetically suspended at a set distance. We want to determine the magnitude and direction of the current in the lower wire. We also want to know if the lower wire is in stable equilibrium, and we want to repeat this process if we assume that the second wire is now suspended above the first due to its magnetic field. So for the first part of this question, we can set the magnetic force on the lower wire equal to the weight of the wire and solve for the current. Now we know the current must flow in the same direction as the upper current for the magnetic force to be upward. We know that the force due to the magnetic field on the lower wire is equal to mu naught times the current I1 times the current I2, which are the two currents in each wire, over 2 pi r, where r is the separation between wires, and this is multiplied by the length of the wire L. Now we know this must equal to the weight, which is mg. So instead of writing mg, we can write this as rho gv, where rho is the density of copper, g the acceleration due to gravity, and v the volume of the wire. The volume of the wire is pi times d squared, where d is the diameter, over 4 times the length L. So now that we've equated these two forces, we know that these forces are equal because the lower wire and the lower wire is in equilibrium, it's not moving. So we can rearrange and we can solve for the current in the lower wire I2. So I2 is rho times g times pi squared r d divided by 4 times mu naught times the current in the upper wire I1. Since all these values are known, we can calculate I2. So if we substitute our values in, this is a density for copper, which is 8,900 kg per cubic meter, times the acceleration due to gravity, which is 9.8 meters per square second, times pi squared times the distance separating the two wires, which is 0.05 meters, times the diameter of the lower wire, which is 1 times 10 to the minus 3, and that's meters, and that's squared. So this is actually d squared in the above equation. And all of this divided by 4 times mu naught, which is a constant, 4 pi times 10 to the minus 7 Tesla meter per ampere, that's the permeability of free space, times the current in the upper wire, which is 48 amperes. And so if we do this calculation, we get I2, the current in the lower wire, to be 360 amperes, and the current flows to the right. So now we have the strength and direction of the lower current. Now in part B, we want to know if the lower wire is in stable or unstable equilibrium. And the answer is the lower wire is in unstable equilibrium. And the reason for this is that since if the wire is raised very slightly from equilibrium, the magnetic force would increase and it'll cause the wire to move even further from equilibrium. So a slight movement of this lower wire would cause the position of the wire to vary indefinitely. And so the wire is in unstable equilibrium. Now for part C, what happens if we take the lower wire and now place it above the first wire? So if it's above the first wire at the same distance, we need the same current, but in the opposite direction. And so I2 would be 360 amperes in strength, but this time the current would be to the left. Now, this is a stable equilibrium for a vertical displacement, since if the wire is moved slightly off the equilibrium point, the magnetic force will increase or decrease and push the wire back to the equilibrium height.